Welcome to Chapter 25 of Openstax Astronomy. This chapter begins our discussions of the largest scales that we're going to cover in this course. If we think about the flow of the course up until this point, we started with a lot of our early chapters thinking about the solar system and scales in terms of how far apart our planets are, and treating our sky as being kind of a fixed sphere, the celestial sphere that went around us, and we didn't have to think about distances in that early part of the semester. Then as we transitioned into thinking about stars more, we started to build up a better understanding of what we mean by large distances on the star scales, distances between stars, how far away they are from Earth, things like that, helping us to realize that our solar system is one tiny little part of a bigger structure. And in Chapter 25, we're going to learn a lot more about that bigger structure, the Milky Way Galaxy. And as we move on to the remaining chapters that we have left, we'll understand that the galactic scales are so much larger than what we've been dealing with up until this point. So that's something to keep in mind as we move forward, is that the intuition we've built so far with how big the solar system isn't helping us so much with thinking about a vastly, vastly larger scale at galaxy levels. So we'll keep that in mind as we move forward. Our first goal in all of this is to think about what we mean by our galaxy, how we figured out that we're part of this larger structure, and then thinking about those main components of the galaxy, terms that we're going to be using throughout this chapter and the others coming up, that will help us make sure we've got the right vocabulary to talk about these topics. So the very first thing we have to understand is that in order to discover that we're inside a structure called the galaxy, we had to figure out a way to determine distances to objects that are far too distant to be able to measure with parallax. So Sir William Herschel and his sister Caroline Herschel attempted to map out stars by basically looking in all directions from their point of view and mapping out how many stars that they could see in each direction. The more stars they could see, the sort of farther out they were looking in the galaxy from their model. The problem is that dust blocks our view, and stars that are farther away will be too dim to see. And so this gives us a kind of fog of war view of our nearby neighborhood, but it doesn't actually tell us much about the size of the actual galaxy as a whole. So it was a starting point because no one up until now had really done much to think about the three-dimensional structure of the stars in our sky, but it wasn't a very accurate method. To be able to think about more methods that we can use to map out the galaxy, we actually have to take a step back to Chapter 19 for a bit and build up our understanding of measurements for distance that astronomers can use. So we've got a pause and think question for us that kind of gets back into our discussion from Chapter 19 when we talked about stellar parallax. So for which of the following stars could we use stellar parallax to accurately measure a distance? So think through the options and pause as usual to think about it. Okay. One of the key things that we need to know or think about from parallax is that the farther away a star is, the less change over the course of the year we're going to see, and so the harder it would be to take a measurement of parallax. We can only use parallax for nearby stars. It is not a magical process that can just get us any distance that we want to. So the answer here is 1. Only the very closest stars to us can actually use parallax, and we need other methods for getting distances for objects farther away. A note here, the Large Magellanic Cloud, that phrase has actually come up when we talked about supernova 1987A. But just so that we have it in our minds, because we'll be thinking about it in this chapter and the next, the Magellanic Clouds are actually dwarf galaxies outside of our Milky Way galaxy. So when you see that phrase, that's what we mean by it. We will be introducing it in a more complete way in a later video. Okay, so back to chapter 19, sections that we had skipped originally, and now we're finally thinking about them. So Henrietta Leavitt was part of the group of women called the Harvard Computers. We talked about that group of women when we talked about Wilhelmina Fleming and Annie Jump Cannon in the figuring out of spectral classes or spectral types for stars. Henrietta Leavitt was also part of that same group of women, and she focused on stars that varied in apparent brightness. Now, when we talked about binary stars, we talked about visual binaries, spectroscopic binaries, and eclipsing binaries. And with eclipsing binaries, we talked about the fact that when a star goes in front of the other, what we're watching is how much light we're receiving, and it seems like there's a dip. Henrietta Leavitt found those in her group of variable stars, but that's a very specific pattern that we can actually tell the difference of and kind of set aside. What she focused on were stars that are actually physically pulsating, getting larger, so more surface area to be brighter, and smaller, less surface area to be brighter, at roughly the same temperatures. She focused on stars in the small Magellanic Cloud. The reason that we want to specify that is because she's looking at stars that are all roughly the same distance away from Earth. And so what she was able to detect was changes in apparent brightness and the length of time over which those changes happened. So Henrietta Leavitt found a very clear relationship between period and apparent brightness. Now, Delta Cephei was the very first one she found, and so all of these variable stars are called Cepheid variables. They're actually one of two different types of variable stars. The other one is RR Lyrae stars. It's outside the scope of the class for us to worry about the differences, and Cepheids are more important to our bigger picture understanding of the historical figuring out of the Milky Way Galaxy. So we're going to focus on those a bit. And it's worth noting that these variable stars are stars that have left the main sequence, so they are no longer stable, they're not in hydrostatic equilibrium anymore, and they're in a very specific part of the HR diagram that's actually for unstable stars, ones that, because of the physics going on in their interiors, are actually getting larger and smaller and larger and smaller. Cepheid variables are among the brightest and biggest of the variable stars, and that means they'll be able to be seen from much farther away than the RR Lyraes. That's important to us, is being able to tell very far away objects. So from that point that Henrietta Leavitt started with, Einar Hertzsprung, the H in the HR diagram, and Harlow Shapley both worked on calibrating this measurement. They found Cepheid variables, so variables that had these same properties, that we also had a measurable distance for, most of which from parallax, but also by tracking their motion over the course of several years. We talked briefly about proper motion, didn't worry about it too much. But they used Cepheids that had a known distance, and what was really important to that is then they were able to change the period apparent brightness or apparent magnitude relation to a period luminosity relation. That's super important. So let's talk through, with this slide, there's a lot going on, let's talk through why that period luminosity relation is so important to us. In the upper left, we have what a backyard telescope could measure for a Cepheid variable star. Magnitude, we've talked about before, is a measure of brightness, and it's just apparent brightness, what the telescope's actually seeing. And it's going brighter, and then dimmer, and then brighter, and then dimmer, in this weird shape that makes it very clearly different from an eclipsing binary system. Now, look at that upper left graph, the magnitude versus time, and pause the video if you need to, but I want you to tell me, either out loud if you're willing to, or write down in your notes, what the period is, how long it takes to go from being the most bright all the way back to the most bright again. So think about that from this diagram. Okay. Again, you can pause if you need more time. But if we look, the first peak that we have on this chart is right around 3 days, and the second peak is right around 9 days. what that tells us is that we've been able to track that it takes 6 days to go from bright to bright again, and that's the period. Then we can look over at the luminosity period diagram on the far right of our slide. And if we trace, and you can even do this on your screen right now, or if you have the printed slides, you can do that. We go to 6 days, so a little bit to the right of 5, and we go up to where all those points are and read across, and what we find is that the luminosity, the true brightness of that star, is about 1,000 solar luminosities. Now, we've not done this calculation in our course, but we have talked about the fact that if you know the true brightness, the luminosity, and the apparent brightness, what your telescope measures, then you can get the distance. We talked briefly about the inverse square law way back in chapter 5, and it came up again later in our slides. But the key thing is that with those pieces of information, we can get a defined measure of distance. And that's what our astronomer is doing in the bottom here. Looking at the telescope, looking at the period luminosity relation, plugging numbers into a computer and figuring the distance out on the board. So now we have a way to get distance measurements to Cepheid variables. Stars are usually on the main sequence. Cepheid variables are fairly rare. But now we go back to what we talked about and introduced last week, star clusters. We talked about the 2 different types of star clusters, and if you don't remember that or don't have those notes, it will be worth reviewing that video. But globular clusters are hundreds of thousands of stars. And as long as we can find one Cepheid variable in that globular cluster, then we can get the distance to that whole cluster. And since they're so bright, we can get distance measurements to very distant objects. So Harlow Shapley did this. He was one of the 2 people that worked on the period luminosity relation. And he made a map very similar to what we see in part B here. And the original Herschel map is the little black outline with the sun centered, kind of like if you ever have a video game map that only shows you what you've just discovered. It's that same kind of thing. The Herschels were able to show us what's nearby, but Shapley's map of globular clusters were able to show us a much less biased view of objects in the Milky Way Galaxy. And so we see that we're actually farther towards the edge of the map rather than right in the middle of it. And that was a really big deal. So the Herschels started this idea that the galaxy could be mapped in 3 dimensions. Someone had to have the idea for people to kind of realize that that was a valid line of thinking and a valid thing to research. And Harlow Shapley was able to use the work of Henrietta Leavitt to determine distances and give us this map that shows us that we're towards the edge of this larger structure. So that was kind of the story, the short story of how we discovered that we are part of our galaxy. And now we can think a little bit more about, from 1920s to now, what we've been able to add to our understanding in the last 100 years. What we now know is that the Milky Way looks very similar to our nearest neighbor, Andromeda Galaxy. The Milky Way is a spiral galaxy, and it has several key components that we're about to list on the next slide. And it's really important to recognize that images like this, true images, will never be of our own Milky Way Galaxy. It may be something that's obvious once you stop and think about it, but you may not have ever stopped and think about it. Our Milky Way Galaxy is so large that it is impossible for us to ever leave it with man-made technology and go back and take a picture of it. It's like trying to take a picture of your house or apartment building while being stuck inside. It's just not possible. But you can take a look at the houses around you or the apartment buildings around you and realize that yours is probably similar on the outside. And that's really what we're doing with this picture here of Andromeda, is saying that that's similar to what our galaxy looks like, and it's giving us the big picture idea. Okay, so the underlined words here are terms that we're going to be using throughout our discussion of this chapter and the next. And so we really need to have them in our vocabulary. When we talk about the disk, we're talking about for all spiral galaxies, most of the gas and dust has settled into a flat, circular-ish disk of material based on the conservation of angular momentum. We don't need to memorize the diameter, but it's useful to have kind of in your notes to think back to. The diameter is 25 kiloparsecs. That number doesn't mean much to us, but 80,000 light years can help us start to think about how this compares to the distances between stars. So, bear with me. 80,000 light years means that if we stood on one very edge of the disk and shined or shone a flashlight, it would take that light traveling at the speed of light, it would take it 80,000 years to get to the other side of the disk. From the solar system to the very closest star is 4 light years. So this is a drastically larger scale than anything that we've confronted in any of our previous chapters. So that's something to keep in mind as we continue. Open clusters, when we first introduced those in our previous chapters, we talked about the fact that they're found mostly in the disk. And so this is reminding us of that. The disk contains all of the young stars in the galaxy are forming in the disk, and we'll talk about why that is in this chapter. And that's where we see open clusters. The halo is a much larger spherical volume that is still what we would call the galaxy. And when we say large with that little asterisk, what that's really trying to indicate is we don't have a clear edge to the halo of the Milky Way. And we'll talk about why that is when we introduce topics a little bit later on in the chapter. But it is where we find almost all of our globular clusters, is in the halo. And they're shown here as the sort of bigger dots of color in this diagram. The central bulge is a portion at the center of the galaxy where stars, rather than being in nice, smooth, lined up orbits in the disk, go in all random directions. And so there is actually a larger group of stars that have more eccentric orbits. And then the very galactic center is also called the nucleus of the galaxy, kind of mimicking the nucleus of the cell. And we'll talk about what object is at the center of the galaxy later on in these slides. This is another picture that may help us think about how the disk and spiral arms relate to the overall shape sideways. So this is a top-down view and a side-to-side view. And what I want to point out here is the sun is shown, is kind of indicated how far away it is from that central bulge region. And it's 26,000 light years. That means it takes light 26,000 years to get from our sun to someone who's sitting at the center of the galaxy looking for it. Kind of cool. So I've mentioned that it's really hard to map our galaxy, and we can't ever take a picture of the whole thing the way that we do with other galaxies. But I want to make sure we understand why it's difficult even to map out the structure while we're within the Milky Way. Distance measurements are really tough. Parallax is the only direct measurement for stars, and everything else that we will kind of introduce as we go along. And the Cepheid variables was the really big addition from chapter 19 that we've just added. Those all rely on being calibrated through the parallax measurements that we can make directly. And then always keep in mind that dust obscures our view, especially as we try to look towards the galaxy and we're looking through more dust and more material. It's harder to actually get a view of the other side of the galaxy compared to where we are. This picture here shows what the galaxy looks like in visible and near infrared at the top and far infrared at the bottom, showing us that there's a lot of dust in the same locations where we see a lot of starlight as well. There's a lot going on in this slide, and mostly I want to include this simply to show that there's a lot more complication that we just don't talk about in this course based on what different types of light can tell us about different structures in astronomy. You can kind of pause and look at this as much as you want to, or look at the posted slides. I'm not going to explain everything that's going on here. That would be a whole other hour-long video. I just want you to look at the fact that each of these different types of light is showing us similar but not identical structures. And that's why astronomers care so much about having spacecraft that allow us to study the types of light that don't make it down to Earth's surface. Okay, we're going to talk about the spiral arms, and then we're going to save the rest of the chapter for a different video. The spiral structure is one that's really interesting to think about because it's hard to map out that whole structure. Again, we're stuck in our own solar system with one view out. How do we have such a good map of what the galaxy looks like? The picture here on the slide we'll see again in a couple of slides. But it is trying to indicate for us the fact that we have this view. This is an artist's representation of our own galaxy. And so we'll walk ourselves a little bit through the kinds of observations that are being made to do this. These pictures here, I'm not going to get into the specific physics behind what astronomers are doing. I just want to introduce the fact that the maps that we make of the Milky Way Galaxy are based on several completely independent and unique measurements that can be made to help map out the spiral arms of the galaxy. On the left here, the kind of weird wispy traces that we have here are maps of neutral hydrogen clouds, so cold hydrogen atoms that are kind of clumped together in clouds. And the way in which they are mapped out is by looking for a really specific wavelength that comes from neutral hydrogen sitting all by itself in space, going from a slightly higher energy situation to a slightly lower energy situation. It has to do with the spin of the proton and electron being opposite or the same. We're not going to get into that physics, and I'm not going to have you memorize that. But 21 centimeter emission, you can read about in the textbook, and it's one of the ways that we can map out where hydrogen clouds are. On the right, we have a map of all of the clouds of larger molecules. So carbon monoxide, CO molecules, they're fairly easy to find. There's not nearly as much CO molecules in the galaxy as there is hydrogen, but they make really specific spectral lines that we can look for. And again, we're not going to get into the details. That's outside the scope of this course. But if we have those clouds mapped out, we can also start to see them clumping together in an arm-like structure where there's clearly places where we have a lot of clouds and clearly places where we have almost nothing. And that's really what I'm trying to convey with these images. Not memorizing the complex physics that we'll not have to use again, but making sure we understand that the map we have of our Milky Way Galaxy is not a just guess. It's based on several different observations that all agree with one another, because that's how science works. The sun is located on the Orion Spur. We don't have to memorize that, but it is kind of interesting because the Orion Spur is named because where most of the material is along that spur, we would have to look in the direction of the Orion constellation to see it. And we've actually confronted the fact when we talked about stars and the family of stars and our stellar census, the fact that the Orion constellation is actually made up mostly of stars that are physically close to us in space. And that's because they're all along that same spur, kind of an offshoot between two larger spiral arms. The current best picture we have of our Milky Way Galaxy, our best model for the Milky Way Galaxy's structure, has two really large primary arms and several fainter ones and spurs. If you look back at scientific journal articles written over the last even just decade, you'll see a lot of back and forth on whether there were 2 arms or 4 arms, and all of that is based on, as we get more observations, we're able to adjust our hypotheses, throw out the bad ones, keep the good ones, and that's what I'm conveying is the current best map that we have, and that's what this picture is. If we look at this larger map, one thing we notice very clearly is that the central region, the central bulge region, is not kind of circular in shape, but it rather is more bar-like. That's actually a specific type of galaxy called a barred spiral galaxy. And in our chapter 26 video, we'll be talking about the different types of galaxies that exist. So the Milky Way is a barred spiral galaxy, and that's worth taking note of. The sun is about 2/3 out from the very center of the galaxy in terms of where we actually see starlight. And so if we had to choose whether it was closer to the edge or closer to the center, it is certainly closer to the edge than it is to the center. We're kind of in the backwaters of the galaxy. Now for the spiral arms, that's the last thing I want to talk about in this particular video. A simple model of the spiral arms is indicated on this slide, the kind of first example or idea that we had that's since been thrown out, is that they were just 2 much larger giant molecular clouds that closer to the galaxy they rotate faster, the same way that Mercury rotates faster than the other planets, and farther from the center it would rotate slower, and so it would kind of get wound up. This model is really easy to disprove because it would mean that as we look across all of the other galaxies that we can see in our sky, galaxies with more rotations or a more tightly wound pattern would be older, and newer galaxies would have less of that spiral structure. And we don't see any pattern like that. So instead, the arms are a spiral density wave. Now let me talk about what I mean by that. The spiral density wave pattern moves through the galaxy. The best analogy I can give is if you've ever been at a sports game with a large enough stadium or arena, and they do the wave, right? In your seat, you see it coming, and when it's your turn, you get up out of your seat, you cheer, and you get back down again, okay? That is a really solid analogy for our purposes at our level for thinking about the spiral arms of the galaxy. Because that stadium full of people is all of the material in the disk of the galaxy. And for the people that are standing out of their seats cheering, they're part of the spiral arms until the spiral arm pattern passes them, and then they're not part of the spiral arms anymore. That's what we mean by that pattern moving through the galaxy. The whole galaxy is rotating, but it's kind of like if we just took that whole sports stadium and just spun it. The wave pattern would still be moving at a different rate through the galaxy. So that's something to keep in mind. The important part of this is what that means is the spiral arms are self-sustaining star formation. Because as we lift up our arms and make a whole bunch of new stars, we make a whole bunch of stars that start to shock the gas around them. So that's why the people next to us are raising their hands and making stars. Is we're basically shocking, we're constantly have this shock wave that makes stars as it runs into material in that region. The galaxy here is a grand design spiral galaxy. It has a nice symmetric circular center. And the redder parts that we see scattered throughout, we've talked about before. Those are emission nebula, and those are coming from very brand new hot O and B stars that are basically in the process of forming, because O and B stars don't live that long. If we see them, then we're talking about a star forming region that's fairly young. And we can see that those red points are mostly in the spiral arms of the galaxy because that's where we're making a lot of new stars. So that's something to keep in mind as we continue, is that the spiral arms of the galaxy are a pattern that doesn't rotate with the galaxy, but rotates at a slightly different speed. And that's where we have brand new stars form. So that's where I'm going to leave us for this video. And we'll pick it back up with the next parts of Chapter 25 in the next video. See you then.